this video, we're going to continue our discussion of interest and look at situations where interest is compounded. So more than likely, you've experienced a situation subject to compound interest. So particularly if you have a credit card, your interest on your credit card is compounded. Essentially what that means is that you are charged interest on your interest. So if you go from period to period and you don't pay off the entire balance, whatever interest was added to your account, you're now charged on that particular amount again. So when we talk about simple interest, we're talking about interest that's only accrued on the principal. In other words, if you take out a loan for a particular amount, that's the only amount that you're ever charged interest on. Another effect of simple interest versus compound interest, say you're charged interest multiple times. Well, if you're looking at a situation where the account is accruing simple interest, you're always going to be charged the same amount. If you're looking at a situation where the interest is compounded, every time you're charged interest, the amount of interest is going to grow. The reason for that is because the interest is what we would say it is reinvested in the account. It's added into the account. So if we go from one period to the next, then the interest we accrued in the previous period is now reinvested in the account. It becomes what we think of as part of the principal. So principal at that point will not only include what we put in the account, but it'll also include the interest that was charged. So the next time we accrue interest, we're charged on the original amount plus the interest we were already charged. That is now considered to be the principal. That's why we end up being charged more interest over time. So again, if you've had a credit card, something like that, suppose you go from period to period and you don't charge anything to your card, you'll notice you still accrue interest. And in theory, if you track your interest charges month to month, you still will potentially be charged more interest than you were the month before. And again, that's because they're now basing the interest calculation on a different amount of principal. They're not only basing it on what you charge to the card, but they're also basing it on amounts that they already charged you that you didn't pay off completely over the previous period. So what we're going to look at here is the practical financial standpoint of this. What do the calculations actually look like in order to determine what your account balance is? So we've got a couple of new variables that we're going to talk about that are specific to compounding that we don't see when we're talking about simple interest. So we're going to let the variable n represent the total number of compounding periods. We can think of a compounding period as a period over which interest is charged. So the total number of compounding periods, that represents the total number of times we're going to be charged interest from when the account begins to when the account ends. So specifically, we're going to talk about situations where if you're talking about a loan, you have something that will officially be paid off. It starts at a particular point and it's paid off. Something like a credit card is a little bit more complicated because it's open-ended. It doesn't end at a specific point unless you choose to close the account. So we're going to have to focus on situations where the account starts at a particular point and it matures and terminates at a particular point. So n is the total number of times that we're going to accrue interest, and then the variable m is going to be the number of compounding periods per year. So how many times you accrue interest per year. So total number of periods over the life of the loan, and this is going to be the total number of periods per year. So our account balance is still represented by the variable a, also called the future value. It's going to be principal times 1 plus I. I is going to be defined as our interest rate divided by m, where again, m represents the number of times we compound per year, the number of interest payments we're charged per year. And what's specific to compounding is that now we have an exponent. The exponent is what causes the interest to grow over each period. The exponent represents how the simple interest is related to compounding in the sense that we're reinvesting the principal each time we accrue interest. So if we were to really look at all the variables in detail, remember I is going to be our interest rate divided by m. We'll talk about the values for m depending on the different situations, how you identify that amount. And then n, we can think of that as m times t, where t is the period of time. So if m is the number of times we accrue interest per year, and we multiply by the number of years we have the account, then that total amount, that product, represents the total number of compounding periods from when the account starts to when the account terminates. Now we're going to use the simpler version of the formula, which means that the starting point for every single problem is going to be to not only identify P and R and T, which we did with simple interest, but also to identify the value for M, which is a variable that is specific to situations where we compound. So let's look at a problem. We want to find the account balance after 5 years if $1,000 is invested at 8%, compounded under these different conditions. So first, compounded annually, then compounded semi-annually, then quarterly, and then monthly. So what's going to be consistent to each of these calculations is going to be, number one, the length of time. We're going to keep the account for 5 years. Number two, the principal, the original amount in the account, that's going to be $1,000. And then also the interest rate, 8%. So what we're changing under these 4 different situations is how frequently we're charged interest. Are we charged interest annually, semi-annually, quarterly, or monthly? Each of these different adverbs, these time-related adverbs, is going to give us a different value for that variable M, that new variable that's specific to the situation where we compound. Now, how do you know if you're solving an interest problem, whether you're looking at a situation where you'd use a formula like this, or whether you'd use the simple interest formula? You're looking for this keyword compound, compounded, compounding, all of these different versions of the word compound. So in some cases, you will be told specifically you want to accrue simple interest. But what if it doesn't say anything? What if it just says you have a particular interest rate? Well, unless you see the word compound or some version of that word, you can assume that it's simple interest. So this word and then one of these modifying words that goes with it is going to be essential to the situation where we're calculating compounded interest. So if you don't see the word compound and then one of these time period words related to that, then you can assume you're looking at a situation where the account is being charged simple interest. Okay, so based on what we have, we know T is going to be 5 years. It is truly going to be 5 because we're talking about a number of years, so T is going to be 5. Our principal P is going to be 1,000, and then our interest rate is 8%. We know we have to convert that to a decimal, so that's going to be 0.08. Remember, take this, divide it by 100, and that's going to give you the decimal form. Now, the value for M, the new value we're going to need to actually determine what each of these account balances is going to look like, that's going to depend on the conditions under which we are compounding. So in the first situation, we want to compound annually. Annually means once a year. So Christmas occurs annually, your birthday occurs annually, you only get one a year. So if it's interest that's accrued annually, that means you're only being charged interest one time a year. So in that case, M is going to be 1. So when I use this particular formula, we know I is going to be R divided by M. So that means we're taking our interest rate, which is 0.08, and we're dividing it up based on how many times we're accruing interest in the year. Now, because we're only accruing interest one time, we're just dividing it by 1. Dividing it by 1 doesn't really change the interest rate, but we're still using this particular formula because of that term compounded, because we're compounding the interest. Now, our exponent is going to be the number of times we calculate interest per year times the number of years that we're keeping the loan, which in this case is 5 years. So our exponent is going to be 1 times 5, which simplifies down to 5. So what we have to do now is we need to simplify this formula. Now, just like with simple interest, there's a couple of approaches you can take to this. You can type it all in one line if you're careful, but you can also type it in multiple steps, and there are benefits to doing it both ways. I want to show you both ways, particularly the way in which you break it down in order to sort of analyze what's happening step to step, and also give you a way to show your work if that's something you feel like you need to do. So let's type it in one line first. Make sure you put in parentheses where they go. So $1,000 times 1 plus R over M, so 0.08 divided by, there we go, divided by 1. Okay, put the whole fraction in parentheses, good habit. Close your parentheses. Now we have to put in the exponent. Go ahead and simplify the exponent so you only have to type in one number. So 1 times 5 is going to be 5. So you're going to type an exponent of 5. So your up arrow represents the exponent right above division. So up arrow and then 5. So double check that you've typed exactly what you want, particularly here with the parentheses. Double check that you closed all of the parentheses. If you didn't, then you need to delete and get back to the point where you can close the parentheses. So the fraction has parentheses, and then the actual parentheses represented in the formula need to be there as well. So double check that. It will change your answer if you don't have all your parentheses where they need to be. Okay, and then we hit enter, and there we go. In general, you're not going to get nice, pretty numbers like you do when you calculate simple interest, and the reason for that is the exponent. So because the number in parentheses isn't a nice integer number, when we raise that number to an exponent, we end up with increasingly complicated decimals. Now, in general, when we're talking about money, the general rule is you round to 2 decimal places unless you're told otherwise. So in this case, if we're rounding to 2 decimal places, that's 3-2. The digit after that is 8, so we're going to round the 2 up to a 3. So that's going to be $1,469.33. Now, what if we wanted to know how much interest was calculated, how much interest was added to the account? Now notice we do not have a formula about interest. We have a formula that allows us to calculate part of the interest rate, but we don't have a formula here that has that variable capital I like we did with simple interest. The reason we don't have a formula for interest is because the interest changes from period to period. We have a formula for it when we're talking about simple interest because the specific amount of interest period to period is always going to be the same. That's not the case with compound interest. So because it's a more complicated situation and the amount of interest is changing from period to period, there's no specific formula we can use to calculate the interest exclusively. So if we want to know how much interest was accrued, we always work backwards. Interest is always defined as where our account ended less where it started. The difference between our principal, where we started with the account, and our account balance, the value the account had at the end of the loan, at the end of the period, whatever you want to call it. So in this case, this is going to be our account balance, and then our principal was $1,000. So the difference between the two, the amount of money that was added to the account, is always representative of interest. So if I take the difference between the two, that's going to give me interest at $469.33. Now, if I were to use these same values, but use the simple interest formula, I would not accrue nearly as much interest. In general, the amount of interest changes, and it changes because we now have an exponent, whereas we didn't have that exponent when we were talking about simple interest. Now, let's talk about how you would type this particular formula in if you want to do one operation at a time. Because again, it's beneficial to think in terms of order of operations. That gives us a way to more closely analyze what's happening from step to step when we apply a formula like this. So let me move this up here. Okay, so if we were to go through this formula, simplify this one step at a time, we want to analyze what's happening with order of operations. What happens in what order? Okay, we always start inside parentheses. Okay, and inside parentheses we have an addition, and then we also have a division. Well, order of operations says the division is going to have to come first, so that means that is going to be the first operation we do. So 0.08 divided by 1, that's going to be the first result. So that now takes care of the division. Now we're adding on a 1 to that, so I'm going to take that value plus 1. Now here's where things change, and this is one of the reasons why I wanted to take a moment to break it down and look at it with one operation at a time, because there's a very common mistake that students tend to make right here. The temptation is to look at something like this and think about the distributive property. The distributive property says that if you have a multiplication out in front of a set of parentheses where there's addition or subtraction, that you can distribute the multiplication to all of the terms in parentheses. Normally, yes, that's true. Technically, you could do that with simple interest. You cannot do that here. The reason you can't do that here is because of the exponent. So let's think about where we stand right now. We've taken care of everything in parentheses. So we technically still have two major operations left. We have the multiplication by the principal, and then we also have the exponent. Well, if we think in terms of order of operations, it's parentheses, then the exponent, and then the multiplication. So if we were to distribute, essentially what that means is we're applying the multiplication before we apply the exponent, which is not allowed based on order of operations. We have to do the exponent first. What you'll find if you do the distribution first is that your numbers end up widely larger, significantly larger than they actually need to be. I'll show you what they actually end up like if you do this incorrectly versus doing this correctly. So suffice it to say, we have to do the exponent next. So the exponent is 1 times 5. So we're going to take our last result and we're going to raise it to the 5th power. Now here's where you're going to get the crazy decimal. Taking something that's non-integer, raising it to a decimal, the decimals become increasingly complicated. Only once you've evaluated the exponent can you multiply by the principal. This multiplication will always be the last thing you do. That's going to be the very last operation that you execute if you're going step by step. So the last thing we're going to do is multiply by that 1,000. Okay, and that's going to give us, again, the same value, because essentially what our calculator did is if we executed the whole formula in one line, it did all of these things, but it just did them behind the scenes. So here we're actually working them out one operation at a time. Your calculator does that, it just does that behind the scenes. Now, just to show you what would happen if you evaluated this incorrectly. So suppose you did everything in parentheses. So keep this in mind, we have it written down. So we did 0.08 divided by 1. Okay, we added 1, and that's everything in parentheses. Now, what I told you not to do, but it's tempting to do, right? It's tempting to multiply right here. So maybe you think I'm going to go ahead and multiply by the 1,000 because that looks right. So I multiply by the 1,000. Well, now I still need to raise it to the 5th power, right? So I'm going to take this and I'm going to raise it to the 5th power. That is the number we get. Now, what does this E mean? E means scientific notation, which technically means take this number, multiply it by 10 to this power. What that means from a practical standpoint is we would take this decimal and we would move it 15 places to the right, and then we'd add in zeros in any locations where we still needed to add in an extra spot for our decimal. In other words, a really big number. It's a big enough number that your calculator can't write it out in one line. It has to write an abbreviated version. So we go from a little, close to $1,500 to a number that's so large that your calculator can't even type the entire thing out. That is the effect of doing the operations out of order. If you do them out of order, you get a number that makes no sense whatsoever in the context of the problem. It makes sense to go from $1,000 to about $1,500. It does not make sense to go from $1,000 to trillions, quadrillions, huge numbers, impossibly huge numbers. So think about whether or not your answers make sense. We're talking about money, so something like this makes sense, whereas that big number in the calculator definitely does not. So pay attention to order of operations. That's going to be important here. Okay, now what happens if we keep all of the terms the same, but now we're calculating interest semi-annually? Now, semi means half, so like a semicircle means you're dividing the circle in half. Semi-annually means you're dividing the year into 2 parts. So that means you're calculating interest twice a year. In this case, M is going to be 2. So all of the other values remain the same because they're based on terms that applied regardless of how we were compounding. The only thing that changes here is going to be the value for M. So I'm going to substitute in all my values. So my denominator, taking your interest rate, dividing it, that's going to change. Now we're dividing by 2. And then my exponent is going to change as well. So before it was 1 times 5, now it's going to be 2 times 5, which is going to be 10. So again, you can type it all in one line, you can go step by step, your choice. Just to save some time, let's just type this one in one line. So 1,000 times 1 plus 0.08 divided by 2. Okay, make sure you close both sets of parentheses. And now we're raising that to the 2 times 5 power, which is 10. So raised to the 10th power. And that's going to give me $1,480, and rounding to cents, that's going to be 24 cents. So notice that the value increased. All of the other conditions for the problem were the same, but what changed was how frequently we calculated interest. And as we've calculated it more frequently, the account balance went up by just a little bit, which also means that the amount of interest is going to increase a little bit. Again, it's our account balance minus our principal where the account started. The difference between the two is defined as our interest. Now what happens if we accrue interest quarterly? Quarterly means 4 times a year. If we divide $1 into quarters, 4 quarters make $1. So that means M is going to be 4. All the other values are the same. M becomes 4, which is changing our denominator here. We're dividing our interest rate into 4 parts, but it's also changing the exponent. So the reason the values are getting larger, notice that this value is getting smaller. If we took 0.08 divided by 1, that's 0.08. If we divide it by 2, that's 0.04. If we divide it by 4, it's 0.02. If this is the component that represents the interest rate, well, it's getting smaller as we compound more frequently. But what's getting larger is the exponent. That's why the actual values at the end of the problem become larger. So how much interest, what's the account balance going to be? So 1,000 times 1 plus 0.08 divided by 4. Okay, close both sets of parentheses. Now our exponent is 4 times 5, which is going to be 20. And there we go, new account balance. Again, just a little bit higher. We went from about 1480 to about 1486. Now what you'll notice is that how much we're increasing by decreases. So what I mean by that, if we went from about 1470 to about 1480, we increased by about $10. Well, then we went from 1480 to about 1486, so we increased by about $6. What you'll notice as we go to the next one is we increase by a lesser amount. So if we're accruing interest monthly, that means every single month. That's going to be 12 times a year. So a new denominator is 12, and then 12 also becomes part of the exponent. So our exponent is now going to be 12 times 5, which is going to be 60. So 1,000 times 1 plus 0.08 divided by 12, close both sets of parentheses, and now we're raising it to the 12 times 5 power, which is going to be 60. And that's going to be our new balance. So about $1,490. So then, actually that's closer to, about $1,490. So we went from about $1,486 to about $1,490, which is an increase of about $4. So as we compound more frequently, the output we get, the account balance we get increases, but it's increasing by a smaller amount each time. Now we don't notice very large incremental changes because we started with a pretty low principal. But say you were to start with $1 million worth of principal, you'll notice more significant changes as you increase how frequently you're compounding, how frequently you're calculating interest. So the fact that we don't notice much here is because this is a relatively small account to begin with. Now, just like with simple interest, we can solve for different values as well, just depending upon the goal for the problem. We're limited here, though, in terms of which ones we can solve for. As soon as there's an exponent involved, it gets a little bit more complicated to solve for other variables. So we're just going to focus on solving for the variable p, which represents principal. So how might we know to solve for p? Well, let's look at that. So if an investment pays 6% interest compounded semi-annually, how much should you deposit now to have $10,000 5 years from now, or $10,000 10 years from now? Okay, so what do we know? Well, we have our interest rate, which is 6%, so that's going to be 0.06 as a decimal. We want to have a total of $10,000 in the future, 5 years from now, 10 years from now, some point in the future. So because that's the future value of the account, that's going to be the value of A. Now, M comes from the compounding semi-annually. This one's typically a little harder to identify because it's not going to be an obviously written number. It's not going to be in actual numerals. It's typically given in terms of words. So the sort of indicator you're looking for is that word compound, compounded, compounding, something like that. And then there will always be an adverbial modifier after that. So semi-annually, that means twice a year. So that means M is going to be 2. Now, what do we still not know? We still don't know T. Well, that's going to be given under 2 different conditions. So here, T is going to be 5 years, and here, T is going to be 10 years, which means the only thing left to find is principal. Well, that's actually what we're solving for. So the question is, how much should you deposit now? Keyword now. What do you want to put in the account today in order to have this much money in the future? Well, the amount you're putting in the account today is what we're calling principal. So that means in this case, principal is going to be our variable. Now we know we're going to use the formula involving this exponent because of this word compounded. Anytime we're compounding, we use the formula with the exponent. If it doesn't say anything about compounding, we know we're going to use the formula that doesn't have one, the one that's related to simple interest. So here's our formula. Let's plug in what we know. So A is going to be 10,000. P is our unknown. R is going to be 0.06. And then M is going to be 2. Okay, so what do we actually have so far? Well, we don't have P, but what I want you to notice is that the number next to P, that's actually just one fixed number. There's quite a few things going on here. There's a few operations, but there's nothing variable right there. So it's just P multiplied by whatever this number happens to be. It's very similar to the situation we were in when we were solving for principal when we looked at simple interest. We have principal and it's multiplied by some number. So ideally we want to simplify as much as we can before we start moving things left and right in our equation. So I want to take all of this, the number that happens to be multiplied by P, and I want to simplify that down first. Now again, you can do it one step at a time if you want, or you could just simplify all of this in one step if you prefer to do that. That's perfectly fine. Now if you do that, make sure you put parentheses and then you apply the exponent outside of parentheses. So that's going to be 1 plus 0.06 divided by 2. There's our fraction. Now close your parentheses for the whole set. And then we're raising it to the 2 times 5 power, which means we're raising it to the 10th power. And that is going to be the number multiplied by P. Now for purposes of showing work, I'm going to round that. But just like with the last problems in the last video, we're going to keep a running total in the calculator so that we don't have to round until the very end. You want to keep your work as exact as possible in the middle so that your rounding at the end is as accurate as it can be. So this is now the number, or technically this, is the number multiplied by P. We want to isolate P. We want to get it by itself, which means anything multiplied by P needs to be divided out. That's going to isolate P. But whatever we do to one side, we have to do to the other side of the equation to keep things in balance. So I'm going to divide 10,000 by this number, or technically this number. Now, rather than trying to retype this though, remember I can access the answer from the previous line using this button right here. So second and negative is going to give me the answer from the previous line. So I'm dividing by the answer from the previous line. It copies and pastes. And then I'm going to hit enter, and there we go. And notice I can round now, but nothing up to that point was rounded. Everything was exact because we just kept the running total going in the calculator. So that's going to be $7,440.94. Now, does this answer make sense? Think about what we were solving for. We were given the account balance, the future value, and we were solving for the principal that would give us that balance in the future. Principal is always going to be smaller than your account balance. So in this case, we're saying if we put this much money in the bank today, then in 5 years, this account will be worth $10,000. And just like with any other problem, if you were to take this and plug it back into the formula, simplify everything on the right-hand side, you should get roughly $10,000 once you evaluate that. Now, what happens if we only want $10,000 10 years from now? What does that mean? What that means is that we're going to give ourselves more time to make the money, to accrue interest. So now what's changed is our value for T. T has become 10. Everything else remains the same though. We're still looking for principal. Our interest rate is the same. And then the compounding is the same because that's based on the actual terms for the account. So the only thing that changes in this next situation is our value for T, which is going to change our exponent. Now, same kind of thing. It's P multiplied by some number. So we want to simplify that number, and that's going to put us in a good position. So 1 plus 0.06 divided by 2, close both sets of parentheses, and then we're raising it to the 2 times 10 power, so raising it to the 20th power, and that's going to be my value. Again, I can round it in order to write things down as I go, but I want to keep that running total in the calculator. So I need to divide that number out. It's multiplied, divide it in order to isolate P, and do the same thing on the other side. So 10,000 divided by this number, or technically this number. So divided by the answer from the previous line, and that's going to give me my value there. So rounded to the nearest cent, that's going to be 76 cents. Now again, does this number make sense? It makes sense again because it's smaller. We're starting with a smaller amount. We're allowing it to accumulate interest so that in 10 years, the account will be worth $10,000. Now, why did the value go down so much? It went down so much because we were giving ourselves more time. Essentially, think of what's happening here as we're investigating the account's value 5 years from now. So here, we're giving ourselves double the time to get to $10,000. If you're giving yourself more time to meet the goal, that means you don't need as much money today. It means there's going to be more time for your actual money to sit in the account. There's going to be more time for it to accrue interest. So you don't need nearly as much money today in order to meet your goal in the future, because more of that goal is going to be met by interest. Whereas if you want to meet the goal in 5 years, you have less time to accrue interest. So more of your account value needs to come from your investment. You don't have as much time to make up the difference from interest. So the more time you give yourself, the less you have to invest now. The less time you give yourself, the more you have to invest now. Okay, one thing I want to talk about now is sort of in the context of the last problem we looked at, where we started to talk about account balances. And we noticed that the account balance continued to increase. The more frequently we compounded, the higher the balance got. But we noticed that it was tapering off. So it was increasing, but every time we increased how frequently we compounded, yeah, the balance increased, but it didn't increase by a lot. So the amount of increase was decreasing. It was kind of trickling down. The question then is there a cap? Is there a highest amount? Is there a type of compounding that we could apply to our account so that we get the highest amount of interest, so that we maximize our account balance? And as it turns out, there is. It's what we call continuously compounded interest. So if you imagine letting n go to infinity, now you can't actually say n equals infinity. Remember, n is going to be the total number of compounding periods. So it could be twice a year for 5 years, which would be 10 of them. It could be 4 times a year for 5 years, which would be 20 of them. 12 times a year for 5 years, which would be 60. If you imagine increasing that value successively, letting n get bigger and bigger and bigger and bigger, letting it go to infinity. Infinity is not a number. We can't actually plug in infinity to a formula. But if you will just imagine letting that value increase as far as it could go, then what you generate is this situation that we call continuous compounding. So essentially what that means is we're literally calculating interest all the time. If we're calculating interest monthly, that means 12 times a year. If we're calculating it daily, that means 365 times a year, or 360 if we're going to use that rule with rounding off. Say we're calculating it every minute. Well, that literally means every minute. You could calculate it every second. Well, we're talking about even faster than that. Continuous compounding means it's literally being compounded. You're literally accruing interest all the time. Now, because you're accruing it so fast, if you think about what happens in the formula for calculating interest, the exponent increases because m has a big value. But if m has a big value, then that also means we're taking our interest rate and dividing it by a really big number, which means the interest rate shrinks so that it's almost infinitesimally small. So every time we accrue interest, the amount of interest we're accruing is extremely, extremely, extremely small. But the fact that we're accruing it so often, so frequently, means we end up increasing the amount of interest overall. And what is going to happen when we do this, which we can't physically do, we can't literally let n be infinity. We can't plug that into a formula. But conceptually, if we were to do that, we generate the highest possible amount of interest based on the terms for our account. So if you look at the same value for principal, same interest rate, same length of time, continuous compounding versus any other type of compounding is always going to result in the highest possible amount of interest. It represents the cap. You couldn't accrue interest worth any more than this particular value. Now, from a financial standpoint, in most cases, this type of compounding described is actually illegal. So for instance, you could not take out a credit card and your credit card company calculates continuously compounded interest. That would not be legal. It's typically used in projection type models. So for instance, stock option pricing something that will be worth something in the future, not knowing ultimately what it'll be worth in the future. Essentially, you're modeling something that could happen, pricing something based on what you're predicting will be the case in the future. But outside of that, we actually see continuous compounding all the time. So for instance, population growth. The populations in the world continue to increase all the time. Our population continues to compound on itself. And so we see these kind of models frequently, but I just want you to keep in mind from a financial standpoint, this particular type of compounding only applies legally in very specific situations. But again, it will ultimately result in the highest possible amount of interest. Now, we're going to come back to that number E. We looked at the number E last couple of videos when we talked about exponential functions. E was a particular base. Remember, it's kind of like pi. It's a fixed number. It's not a variable, and it just pops up from time to time. This is the application that E really applies to. It applies to continuous compounding. So our formula for calculating our account balance when we compound continuously is not going to be the same as the regular compounding formula. The reason it's not the same is because think about where n is. N is our exponent. Well, for letting n be infinity, how do we plug that in? Infinity is not a number. We can't plug in infinity to a formula. So there's not really a way to use this formula if we're saying that n is essentially infinity. So the formula has been adjusted, and it's a very complicated discussion to get into to explain how these two formulas are related. Suffice it to say, they're related by something that requires calculus to discuss. But if you just imagine letting that value of n increase without bound, get bigger and bigger and bigger and bigger, then the regular compounding formula essentially converts to this formula with this value E. Remember, E is approximately 2.718, but you have a couple buttons on your calculator for it, so you're just going to use those buttons. So you'll notice that M disappears. Since N is now something that we don't really have a value for, M is also something like that. So all we need now are the same values that we had for simple interest, but we're using this formula instead. It looks like PERT. So principal times E raised to the RT power. Now, just like with the regular compounding formula, if you were going to simplify one operation at a time, multiplying by the principal will always be the very last thing you do. So you'll take your E, you'll raise it to the R times T power, and then you'll take the result of that and multiply that by your principal. That will always be the last step in your problem. So let's look at an example. What amount will an account have after 2 years if $5,000 is invested at an annual rate of 8% compounded continuously? Okay, compounded continuously, there's my red flag. So compounded tells me automatically I'm going to be using a formula with an exponent. The fact that it says continuously rather than quarterly, monthly, daily, something like that, that word continuously means we're using the formula involving E. So learning how to read the problems and interpret those key words is going to be really important. Compounding means there's an exponent. Compounding continuously means it's this specific formula and this formula exclusively. So that means we need P, R, and T because we're looking for the value of the account in the future, which represents the value for A. So our length of time is going to be 2 years. We've invested $5,000, so that's going to be the amount of principal. And then the interest rate is going to be 8%. So that's going to be R, convert it to a decimal, that's 0.08. So I'm going to plug in all my values to the formula. Now remember, E is not a variable, it's a fixed number. It's a button you're going to find on your calculator. So just like before, I want to show you how this would work, calculating it both ways, both all in one line or if you wanted to go one step at a time. So let's do it in one line. So 5,000, and then we're going to multiply by E to an exponent. Now remember, you can get E in two places. There's an E right above the division button in blue. That's just plain old E. And then also right above the LN button, there's E, but that E automatically has an exponent that goes with it. So since we're going to have to type an exponent, we might as well use the version that already has an exponent. So second and LN is going to give me that E, and then it's going to open an exponent for me. Now, depending on how new versus how old your calculator is, it may format the exponent like this, or it may just draw an up arrow and then maybe open a set of parentheses. If it just opens up a set of parentheses, then you want to make sure you put parentheses around the entire exponent that you type. And I'm going to do that here just to be consistent. It's not going to be as important if the calculator truly formats the exponent, but just to be consistent so we're all typing the same thing, it's not going to be a problem to do that. So I'm going to put parentheses, and then in my exponent, I have two things. So 0.08, and we're multiplying by 2. So 0.08 times 2, and then close parentheses, and that's my exponent. And then I hit enter, and that's going to be my balance. So $5,867.55. So if we wanted to know how much of that was interest, same thing in any situation. Interest is always the difference between where we end up in the future versus where we started now. Any additional amount in the account is representative of interest. So our balance minus our principal, the difference between the two, that's going to be the value of interest in the account. And since this particular account was subject to continuous compounding, what that means is that this is the absolute highest amount of interest that we could earn on any account that was subject to these values. So simple interest subject to these values would be the lowest amount of interest. And then if we compounded annually, semi-annually, quarterly, the amount of interest would continue to increase, but this is the absolute maximum amount of interest that we can accrue on any account with these particular terms. Now, if we wanted to type all of these operations one at a time, what would that look like? Well, what do we have going on here? We've got three things. So we have P being multiplied by this whole factor, e to the RT. So p is multiplied by that whole thing, kind of like with the other compounding formula, p is multiplied by the whole thing that's being raised to the exponent. Well, then we have r times t inside of the exponent, and that becomes the exponent for this base of e. So we really have three things going on. So if we want to go step by step, we have to execute three different operations. So the first operation we'd have to do is to multiply r times t. Because that whole expression represents the exponent for e, we can't use it as an exponent until it's fully simplified. So the first thing I would want to do would be to simplify the values in the exponent. So 0.08 times 2. That now represents my exponent. Now sometimes it'll be fairly simple like this, sometimes it'll be relatively complicated. Ultimately, it doesn't matter, because remember, you have that A and S button. Anytime you want to bring up the answer from the previous line, copy and paste it, you can use A and S, and that'll do it for you, so you don't have to retype anything. So the next thing we need to do is we need to use that exponent and apply it to the base of E. So I'm going to type in my E. Remember, second and ln is going to give me E with an exponent. And then rather than typing 0.16, which I certainly could do, I just want to copy it into the exponent using that A and S button. So second and negative is going to copy the answer from the previous line, but it's going to copy it into this exponent. Now again, depending on how your calculator formats the exponent, it may draw the up arrow and then put some parentheses. Just do the same thing. You do the same thing, close your parentheses, and then you have the same thing here, even though it may look a little bit different. So now I'm going to hit enter, and now that gives me this particular value here. So E evaluated with that particular exponent. The final operation is then to multiply by 5,000. So always, you'll notice for every single formula we've executed, this is going to be the last step, multiplying by the principal. So times 5,000, and there we go. Same answer, no change, just operations one at a time. And so the interest, of course, will also be the same. Now let's look at the opposite situation. So we've also talked about how we'd solve for principal. We can do the same thing here. So if an investment earns 9% interest compounded continuously, how much should you deposit now to have $25,000 36 months from now and 9 years from now? Okay, so what do we know? We know we're compounding continuously. Okay, so that's going to tell us this formula is the one we want to use. We know our interest rate is a 9% interest rate, so R is going to be 0.09. And then the question is, how much should we deposit now in order to have $25,000 at some point in the future? So $25,000 is the account balance we want to reach, so that's going to be our value for A. And our question is, what do we deposit now in order to meet this goal in the future? So that means principal, P, is our unknown. That's what we're trying to solve for. So I'm going to plug in what I know to the formula. What am I still missing? I'm still missing my value for T. Well, we're looking for T under two different sets of conditions. So in the first situation, 36 months. Well, this one's maybe a little bit tricky, because we're talking about months, we're not talking about years. But remember, you can always write months in terms of years if you write part over whole. So in this sense, you can think of 36 months as the part. Well, what would the whole be? Well, the whole is always going to be the value based on that period of time for 1 year, which is going to be 12 months. So our fraction would be 36 months out of 12 months for the year. And if you do that division, that's actually 3. So 36 months is really the same thing as 3 years. This would be true regardless. So say it was going to be 30 months. If you wanted to do 30 months, convert it to years, you would just do 30 divided by 12. That would give you the number of years you'd want, which would be 2.5. Or if you wanted to do it in fractional form, convert it to a fraction, that would be 5/2 as your value for T. So same kind of thing, always part to whole if you're talking about a different unit of time other than years. So that is going to be our value for T. P is our unknown, and then we have our value for R and our value for A. So A is going to be 25,000. R is going to be 0.09, and in this case, we're letting T be 3. Okay, now just like the last one we looked at where we solved for principal, notice principal is being multiplied by just constants. It's an expression that then can be simplified, and it's just a single value being multiplied by P. So we want to simplify that part first. Remember, E is not a variable. So second, and ln is going to give us E, and then we're raising it to the 0.09 times 3 power, and that's going to give us this particular value. So that's now the value that's being multiplied by P. We need to divide it out from both sides in order to isolate P. And you'll notice what I wrote here looks a little bit different. If you imagine taking P and just dividing this expression out from the very beginning rather than simplifying it, if you recognize that E to the 0.09 times 3 power is just a fixed number, you can divide that whole thing out in its non-simplified form, simplify all of this at one time, and you'll still get down to the same answer. But if we want to do that part first, if we want to simplify all of that first, this is going to be the value that we get. So that's what we're now dividing into 25,000. So 25,000 divided by this particular number, which we can pull up using second and negative, pull the answer from the previous line, and then do that division, and there we go. So $19,084, and if we're rounding to cents, that's going to be 49 cents. Okay, as always, we want to make sure that the answer makes logical sense. What were we solving for? We were solving for principal, the original amount in the account. In this case, we want to get to $25,000 in the future. So in order to do that, we're starting with a little bit more than 19. Principal is always less than the account balance. In this case, this would be the amount of money we need so that it could sit in the bank for 3 years and make it to $25,000 in the future. Okay, now what if we give ourselves more time? What if we gave ourselves 9 years instead of 36 months, aka 3 years? Well, in theory, we shouldn't need nearly as much money. If we're going to let it sit in the bank for longer, it has more time to accrue interest, so we need less now, and we're going to make more of our goal from interest than we would in this particular situation. So the only thing that's changing here is our value for T. T is now going to be 9, but all the other values are associated with the actual problem description. So A is going to be 25,000, R is 0.09, and then our value for T is going to be 9. So structurally, this is exactly the same. P is now multiplied by this particular constant value. So let's simplify that. So that's going to be E raised to the 0.09 times 9 power. So that's now the value multiplied by P. Notice that that's a bigger number than it was for the previous one. So you probably cleared that out, which is fine. But if you think back to what that was 1 and some fraction. This is 2 and some fraction, which means when we divide it out, we're now dividing the 25,000 by a bigger number, which results in a smaller quotient. So that's how the number mechanically is going down. So we're going to divide that number both sides of the equation to isolate P. So 25,000 divided by this particular value, divide it out, and that's going to give us the new account balance we need. So $11,121.45 will be our starting account balance in order to have a balance of $25,000 9 years from now. And again, it makes sense that this is a smaller number than this one. Here, we have 9 years to get to our goal. Here, we only have 3 years, so we have to have more money up front in order to meet the goal. Okay, so the last thing we want to talk about is comparing options. So what are we comparing? Well, suppose you have different investments or different loans available to you and they have different kinds of terms. So we're looking at things from the standpoint of compounding. What happens if you have 2 different things? What if both your interest rate and your terms for compounding differ? So how might that look? Well, you might have a higher interest rate, but not calculate interest as often. Or maybe you have to sacrifice a little bit of your interest rate, but you get to calculate interest more often. Because remember, those were the two things that kind of balanced out when we looked at all the different ways we could compound. As we compounded more frequently, in general, we ended up with more interest. But what if the more frequent compounding is then balanced out by having a lower interest rate? How do you determine what's going to be better terms? So if you're investing money, of course, you want to make money. The more interest, the better. If you're taking out a loan, you want to have lower interest because that's ultimately money you're going to have to pay back. Well, it's not literally a one-to-one comparison. You can't say higher interest rate is always better. You can't say more frequent compounding is always better in situations where both of them have been altered. So in order to compare investments, since we can't make that one-to-one comparison, what we do is find what we call the annual percent yield. Essentially, this is taking the compounding terms and it's converting them to a corresponding simple interest rate. It takes all of the terms in terms of compounding per year and it synthesizes all of that together and it converts it to the same particular rate that you would have to charge an account in order to be charged simple interest and end up with the same account balance at the end of the year. If you can calculate this particular value for all of the different account options, then that's going to allow you to make a one-to-one comparison among all your different options. Whatever the higher interest rate is at that point, that's going to be the most interest. Whatever the lower annual percent yield, corresponding simple interest rate, that's going to be the one that gives you the lowest interest. And again, if you're talking about an investment, you want the highest amount of interest. If you're talking about a loan, all other things the same, you want the lowest amount of interest. Now, ultimately here, the principal is not going to matter. The actual amount of principal doesn't matter because all we're talking about is how the interest rate and the compounding terms would affect a principal. So as long as we were talking about the same amount of principal being invested in all of these different possible accounts, that specific value is not going to make a difference. Ultimately, the best account is going to be the best account regardless of how much principal you have to invest. So some principal is being invested and we need to know our annual interest rate R. And then of course we'll need to know the compounding terms because we're comparing R and its compounding terms among all the different combined options. So we have an annual percent yield formula for regular compounding, for periodic compounding, annually, semi-annually, quarterly, etc. And then we also have a way of calculating it when we're compounding continuously, because that of course is a possibility as well. So if we're periodically compounding M times a year, remember that's going to be the value that we get when they describe how our account is compounded. This is going to be our annual percent yield. That is going to be the value that represents the decimal form of our particular interest rate if we were to think of it in terms of simple interest. So a lot of it looks similar to what we see when we look at the compounding formula. Notice what's in parentheses is exactly the same as what's in parentheses for that standard compounding formula. What changes is the exponent and then what we do after that. So in the normal compounding formula, the exponent is M times T. Well, here we're just talking about a rate that applies to a single year. So you could kind of think of there being a T there, but T is just automatically 1, so you don't actually see it. Now from this value, we're subtracting 1. It's almost like subtracting out this 1 in a sense. So what does this really mean? Well, this represents how the interest is accrued. This is the particular factor that's applied to the principal, so it determines how the interest is accrued. You can think of 1 as kind of representing 100% of the principal. This is going to be a number that's bigger than 1. So if you take this number that's bigger than 1 and subtract out 1, then the difference between the two is going to be the particular fraction that adds the interest to the account. So whatever that value happens to be, that value is going to show you how the account's balance increases. So subtract out the 1, which means get rid of the 100%, which represents the principal you started with. And whatever's left over, that's going to be the fraction that accounts for all of the increased values in the account. Now, if you're compounding continuously, similarly, notice we're almost multiplying by the same thing that we multiplied P by, except we don't have a T because T is understood to be 1. And so this is going to be the factor that increases our account balance. And then we're subtracting 1, and 1 means the exact same thing here. We're taking whatever this number is, subtracting the 1, which represents 100%, and whatever's left over is the particular factor that increases our principal by a certain amount and adds the interest to the account. So once we find these particular values based on the terms for our accounts, that's going to tell us what the simple interest rate would have to be to get us the same amount of interest at the end of the year. And it's going to give us values that we can actually compare one-to-one if we're looking at different investment options. So let's look at an example. So the table below lists the interest rate and the compounding period for CDs offered by 3 banks. We want to determine the annual percent yield for each and then compare the investments. And we're going to round each percentage to 3 decimal places. Now ideally you'll just keep the running total in your calculator, so rounding will never be an issue. You just round at the very end. So we have 3 different options, 3 different banks. You'll notice all the interest rates are different, and then all of the compounding terms are different as well. So 4.95% compounded daily, which is really frequently. Okay, if we increase the rate, the next bank offers a higher interest rate, but we're not compounding as often. You don't get interest as many times a year. And then the last bank offers the lowest interest rate by far, but the interest there is compounded continuously. So what we want to know is what's going to be the best option in terms of yielding the highest return, the highest amount of interest. And so rather than saying the highest interest rate is best or the most frequent compounding is best, we calculate this annual percent yield, and then we have something that we can compare truly one-to-one. So let's start with the first one, the deep green bank. So our annual percent yield is going to be 1 plus R over M. Well, here our interest rate is 4.95%. So 4.95, convert it to a decimal by dividing by 100. So 0.0495, that's going to be our interest rate. And then we're compounding daily. So we'll just divide by 365 here. If you're told to divide by 360, you can do that. Let's just do 365 here. So daily is 365 times a year, which means the exponent is also going to be 365. And then from that, we're going to subtract 1. Okay, so we want to type all of this in, and let's see what that comes out to. So in parentheses, 1 plus 0.0495 divided by 365. Okay, close your parentheses. Close your parentheses again so that the exponent is applying to everything. So we're raising that to the 365th power. Now be very careful here. You can't immediately type -1 because notice you're still in the exponent. So if you have a calculator like mine that formats your exponent this way, you just want to arrow out, and then that will take you back to the entry line, and then you can subtract 1. Now, if you have a calculator that doesn't actually format an exponent, remember the ones that just type an up arrow and then parentheses, just make sure to close your parentheses after the 365, and then you can type -1, and it will interpret the way, your calculator will interpret it the way you want. So then hit enter, and there we go. Now that's the decimal version of this rate. So to convert from percent to decimal, we divide by 100. So decimal to percent, we're going to multiply by 100, which gives us 5.074% roughly. What does this mean? This would be the annual interest rate in order to get the same amount of interest if we were only charging simple interest. So 4.95% compounded daily would be the same thing as 5.074% interest calculated just based on simple interest. Okay, so let's compare it. What's going to come next? Next bank. Now the next bank has a higher interest rate, but they only compound quarterly. So make sure the rate is adjusted, and then we're also adjusting the value for M. So our rate was 4.97%, so we're dividing by 100. Okay, that's going to be the decimal version. So that's going to be plugged into our formula, and then again, m is going to be 4. So 1 plus 0.0497 divided by 4. And don't make the mistake of forgetting to change the interest rate. If you forget to change the interest rate, then this one will obviously be better than this one, because this one you get interest more often. So make sure both parts are being changed, both the rate and the value for m. Okay, close your parentheses. Now we're raising that to the 4th power. Notice these two values are always going to be the same. Now make sure you arrow out of the exponent or close your parentheses for the exponent, and then you're going to subtract 1. So that's the decimal times 100 is going to give you 5.063%. So far, the first bank is going to be the better option because that's going to give you a higher return. So 5.063% interest versus 5.074% interest. Now suppose it were a loan instead. This would be the better one because that means less interest overall. So it just depends on what kind of situation you're in, whether you want a higher interest rate or if you want a lower interest rate. So far this is the better one, but we still have another one. So last bank, Liberty Bank, we have the lowest interest rate, but we're compounding continuously. Now don't make the mistake at that point of using the same formula, because when we're compounding continuously, remember the interest formula changes, the account balance formula changes, which also means that the annual percent yield formula is going to change as well. So it's going to be this formula. It's going to be the formula involving E. So E raised to our interest rate. So 4.94%, 4.94 divided by 100. That's going to be the decimal version of our interest rate. So it's going to be E to that power. So you can either retype it or second and negative, just copies and pastes the answer. Now as before, get out of the exponent and then type -1. And then we want to multiply by 100 in order to get the percentage. So 5.064%. So this is going to be the next best option. So the highest return comes from the first bank that has the in-between interest rate but compounds daily. And then the lowest return is going to come from the second bank, Charter One, that has the highest interest rate but calculates interest less frequently, which would potentially be a surprise. You might look at this and think, highest interest rate, automatically going to be the best option. But in this case, it actually turns out that was the worst option. That was the least return overall. So one thing that I haven't really stressed, but I want you to keep in mind for these last two sections, we looked at simple interest and we've looked at periodic and continuous compounding. One thing I want you to keep in mind that's implicit, that we don't really discuss, but we need to mention, we need to point out. We're talking about accounts that start with a particular value, end with a particular value, and there's no changes made in between. The only changes made to the value of the account come from interest. So what we're not considering are situations where you might be adding your own money to the account. Or if you're talking about a loan, making periodic payments to pay off the loan. So what we're talking about if we're talking about an investment is you take all your money up front, you dump it into the bank, and you just let it sit there and collect dust. We're looking at how much dust, if you want to call it that, how much dust is in the account other than what you put in there at the end of a certain time period. But again, we're assuming that you did not touch the account, that you didn't add anything, and that you didn't take anything out. And then from the standpoint of a loan, we're assuming you took out a loan from Mattress Mac and you didn't have to pay off your Tempur-Pedic for 5 years, whatever. So you paid off the whole thing at the end of 5 years. So you didn't make any periodic payments. You just paid one lump sum at the very end. So all of these formulas that we've looked at so far operate under those particular assumptions, this idea of a lump sum. Now we know that's not necessarily going to be the case for accounts in real life. You add to a savings account and that's a good thing to do. but how does that actually affect the balance, and how does it affect the way interest accrues? And then specifically with a loan, the likelihood that you're going to get a loan every time that you just pay back at the end of 5 years, the likelihood of that is pretty low. In most cases, they calculate the value for the loan up front, and then they give you a particular payment plan. You meet all those payments and you pay off your loan, but you're decreasing the value of the loan over time rather than just writing a big check at the end. So what we're going to talk about in the next couple videos are the kinds of things that have to happen if we're going to make periodic payments over time. We're going to use some of the same ideas, particularly these ideas related to compounding, but we're going to have to adjust the formulas because things like principal are going to change over time. There are going to be more things changing in the account than just the balance based on interest. If the balance based on principal is also changing, then we're going to have to look at some new and adjusted formulas.